Welcome to this introductory series of training videos for SolidCAM. This video's topic is creating a new turning or mill turn cam part. So for the setup of a new cam part, first we're going to open up the original solid we're programming off of. In this case, it could be an original SolidWorks model, or it could be a translated solid from a third-party format. Once it becomes SolidWorks geometry, we can program off of it. To add SolidCAM to that, we can either go to Tools, SolidCAM New, or we can go over to the menu over here and we can click SolidCAM New. So we actually have mill turn and turning, and the reason there's the two is one is for just turning, just side one turning, and the other one is mill turn. It can program for a mill turn or a lathe. With the lathe, it actually has the full functionality of the module, which would allow you to do side one and side two. And since majority of the time we're looking to program the entire part in one CAM part file, we recommend using the mill turn module. That way you can get the full functionality of the software and you're still doing the turning operations that you were looking to do. Even though you're choosing the mill turn module, the post that you end up selecting will limit you to the turning operations. Let's do that. Let's click the mill turn. And first selection here from the first window is, are we working with external or internal SolidCAM files? If we click on internal, what we're actually doing is adding a folder to the SolidWorks file that contains our tool tables, our operations, pretty much anything to do with the programming will be added to the original SolidWorks model. If anyone who doesn't have SolidCAM opens up the SolidWorks model, they'll still see the folder, they just won't be able to access the programming stuff. So it is the original SolidWorks model that you're working with. And that makes it easy for file management. You can upload it to a network location. You can load it into a PDM or a Vault style software. It makes it easy because it's one file and it contains everything. The drawback is that it is that original file. So this being a SolidWorks part file, I cannot add additional solids for vices, clamps, soft jaws, tailstock, anything like that. So it is limited in that way. If I would like to have the full functionality of the software, I can go with external. What external actually does is it creates a SolidCAM only file. It's a file that basically takes a copy of the solid model, relabels it as design model, so it's your copy of it for programming, but it remains associative to the original model. So even though you're still programming off of a model, that model is a copy of the original, but because of the level of associativity that we maintain, any changes to the original model update your copy of it, and then they will update your toolpath as well. And SolidCAM External is actually a type of assembly file. So it now has the ability to add in the vices, the clamps, the soft jaws, the tailstock, unique stock, anything you're looking to add to the model to better simulate it, to better program it. It being a separate file, and you have a copy of the model, you can make changes to it in terms of the design. So if you don't like this sharp edge and you like to make a fillet or a chamfer on there, you can actually go in there, make that design change, and that design change is not seen by the original design model. So it's your copy for programming, but any changes on the original design side, you will see as well. So the full ability of the functionality of the software is there in terms of associativity. It's just that you can modify the model and then the original design doesn't see it. So you contain everything you need in this one part file. So since it's the most powerful of the two, we're going to go with that one and we'll display that in this video. It will be a separate file, so we need to give it a name. And the name generally is the same name as the original SolidWorks model. But in this case, because I've used this file a couple of times, it's added a -2. I'm just going to give it a 00 there. So that will be the name of the separate SolidCAM file. That'll have an extension of PRZ. And it'll be saved in the default location. If I leave that box unchecked, it'll just be saved in the default location where I keep all my CAM part files. That default location is listed in the global settings. So to see where you can change that location, I'll refer you to the global settings setup video in this series. If you don't like where that is for this particular part, you can click Browse. You can browse to whatever folder location, either on your network or on your hard drive, that you'd like to save the file. But if you'd like to save this SolidCAM file side by side with the original SolidWorks model, then you can just click on this box. And it'll actually change this address to the same address as the original SolidWorks model. You can see that it changes the name back, so I'm just going to change that back as well. And lastly, the units that we'll be using for this CAM part. So another benefit of the external format is if the original SolidWorks model needs to stay in metric, but you need to program for inch, In your external file, you have full control over everything. You can tell it that you're now programming and measuring in inch just by changing it here. So we'll go with external with these settings. Once I click the green check mark, it actually closes the original SOLIDWORKS model we were looking at, opens up a copy of it inside of SolidCAM External. The SolidCAM External file takes the name that I gave it of in this case, simple turning -00. You can see that it has the assembly solid there. So this is actually a type of assembly that allows you to add those additional solids. The original model was relabeled as design model, and you can see that it has all the features in there. So this is a model that I can manipulate for better programming, for more machinability. Any changes I make here do not go back to the original solid. Everything under design model does actually read from the original solid. So the associativity goes from design to programming, not from programming to design. So you have the ability to make your own modifications as well as read modifications on the design side. Since everything under design model is associative, there might be some things you want to add that are not associative, that you do not want to be overwritten when there's a rev change. So that's why it's given you this second solid called CAM. CAM is actually just an empty solid. It has the planes and has the origin, but you can add your sketches under here and they will not be overwritten by the associativity. And on top of that, this is still a type of assembly file. So if there's anything you want to add on top of these, you can easily go to assembly and then insert components. This still operates like a SolidWorks assembly. We are still inside of SolidWorks. We can still use that functionality. So let's get into the actual programming. So on the left side here, we're looking at the definition of this CAM part. And the first thing we're going to define is the post processor that we'd like to use. And you can see that SolidCAM comes with a couple of default ones, but it's usually advisable to contact our post processor team and give them the details of your machine so you can get a custom-made post for your machine. This is even more important when you're doing mill turn because there's a lot of cycles, a lot of additional functionality outside of operations that you'd like to do with your post. Things like bar feeders or part transfer. A lot of that can be tailor-made for the specifics of your machine just by giving the details to our post team. But I'll go with my DMU 80 for now. Another thing, remember that we're inside of the mill turn module, but I can choose lathe posts. You'll see there's some lathe posts on there as well. So the module is mill turn, but your post processor dictates what you're able to do within this module. So if I choose a lathe post, I'll only have access to turning operations. Next is coordinate system. So the coordinate system here is the offset on the machine. So on the machine, if it's G54, if it's P1, E1, whatever it is in the G code, within the software, it's going to be MAC1 position 1. The MAC number translates to the offset, and the position is just the index position of that setup. So literally MAC1 position 1 will be XYZ, ABC, all at 0. If you have a MAC2, you're outputting the second offset. MAC3 is the third offset. If you've defined positions 2, 3, 4, so in this case MAC1 position 2, MAC1 position 3, what you're doing is you're defining an index plane of the part. So you'll see that in the subsequent videos on our YouTube channel or in this introductory series on how to do some of those index planes. But for now, just to basically set this up, we're going to do MAC1 position 1, which is the setup coordinate system. And to do that, we have the 5 options in this list. Really what you're doing here is selecting one of the choices in this list based off the geometry you have available to you. And a lot of this is more for the milling side because this is the same interface we use for the milling, but for turning, it still has its functionality. So we'll start from the bottom here. By 3 points allows you to choose a origin, a point in the X direction, and a point in the Y direction. This is based solely on sketch points or vertices because maybe your solid doesn't have any cylindrical faces or flat faces to help you to define your coordinate system. So you're going to be using sketch data. You can program a turning operation off of a simple sketch, a translated DWG or DXF, just by using this option here. Likewise, define, the second on the list, actually does the same. This time though, instead of just choosing points, you can choose a line for the X direction, a line for the Y direction. As soon as you have X and Y, you have Z. So this can also help you to define your turning parts if you have just sketch data. Normal to current view is more for 5-axis work. So if you're working on a mill turn that actually has some 5-axis capability, you actually can eyeball your part And if you see an angle in your point of view that looks like it would be perfect for an index position for your operations, your 5-axis operations, then what this does is it takes a snapshot of the screen. The z-axis comes out of the screen in your point of view because the z-axis would be your tool axis. X positive goes to the right of the screen, the Y positive goes to the top of the screen. Again, this is more for 5-axis work, so you'll see that used if you don't know what angle the part needs to be at. You can always just take a snapshot of the screen and create that coordinate system. Select coordinate system actually opens up this menu down here where it will allow you to translate SolidWorks coordinate systems into SolidCAM coordinate systems. Again, this is a brand new part file, so we have the ability to redefine everything in terms of directions and such. A good example of that is if we look at this part, it actually is aligned in the x-axis. And for turning, that's not actually what we're going to do. We need that to be aligned in the z-axis for turning. So when you create your own coordinate system, you create it inside SolidCAM for the purposes of SolidCAM. But if there was a SolidWorks coordinate system that you wanted to use, let's say, for instance, it was part of the design and it has to be set up a certain way, then you can just select from the SolidWorks coordinate systems and translate it. But the one that's more often used in mill turn and turning is select face, because what you can do with select face is orient the toolpath based off of a revolved face. Now, the other options in here allow you to use flat faces, but again, they're more for milling. So if you actually are trying to use these, I would refer you to the Getting Started in Milling Operations in the other playlist on this YouTube channel. But for turning, majority of the time, it's recommended to use center of revolution face, because if there's a part that you're looking to turn, there's definitely some sort of central axis that you want to revolve around, and usually that will be defined by the revolved faces here. So I just need to click on any one of these revolved faces. You can see that it places a coordinate system dead center. So that z-axis is actually the rotary axis of that face that I selected. And it's on the wrong side. I actually want to program on this side first. So I'll do a change to opposite. And you can see that z equals 0 is placed on the very front face of that part, and the x-axis is pointing radially. So this is perfect for turning. Another rule of thumb here is you would usually like to put your x-axis at pointing at the first milled feature. That way, if you're doing production, you don't actually have to index it every time to get to a flat or a drilled hole. Or in this case, I'd like to be able to locate off of that keyway once it's made. I'll just get the keyway to be at the 0 degrees or the 12 o'clock position. So I just need X to go that way. And that's what the rest of this menu is for. If you take a look at all the other options here, this is just to further modify the location of my coordinate system. So when I clicked on center revolution face, it placed my origin dead center on the front face. So that's z equals 0 face right there. But I probably don't want that to be z equals 0. I need some material on that front face. So I'm going to go to modify by delta. And I'm going to add 20 thou on that front face. As soon as I click my mouse somewhere else, you can see that coordinate system shifted by 20 thou. I was mentioning that I want the x-axis positive to be pointing towards the first milled feature. I want to point at that keyway. So I'm going to go to modify by flip, and I'm going to flip around the z-axis. So I'm going to rotate that coordinate system around the z-axis 90 degrees with each click. And that points the x-axis at my keyway. If the keyway was not exactly at that 90-degree rotation, I want to get to that exact rotation there. I have pick the x direction that would align my x-axis with whatever line I chose. I can actually give it a proper angle over here under modify by rotation. So lots of different options in here to align or to locate your coordinate system off the part. So with that done, I'm going to click the green check mark, and that confirms that as Mac 1 position 1. Okay. Now, if I go back into the coordinate system manager, you'll see that it's Mac 1 position 1. Now, for this part, I'm actually looking to do both sides. On this simple mill turn, I'm actually having it in the jaws being held here, and then I'm eventually going to take it out, flip it, put it back in the jaws, and then this will be the face that I need to machine. So I need a Mac 2 on this one, and that's why we choose the mill turn module. I can go to add, and now it'll allow me to add a second offset. So I'm going to define this as Mac 2. That'll be the second offset on my machine. I'll use select face, center revolution face. Again, I'll just click on one of these rotary faces. Maybe I'll click on this one this time. And you can see that it places the z-axis pointing that way. The z-axis is always your tool axis. And in turning, we need it to point like that. I still want that to be pointing at the keyway, so I'll do a flip around Z. You can see that guy is now set up. We'll just set this guy as the Z0 face for now. So with my coordinate system set up, now I can go to the rest of the definition. And the rest is things like the stock and the target. So the stock is actually the raw material we're going to make this part out of. And in turning, that could be your bar stock, that could be a casting that you're spinning, that could be many different things. And we have all the options, again, here to help us with whatever type of geometry we have in front of us. So for turning, you actually have all the functionality here that you had on the milling side as well, but you can use whatever you need for turning. So let's start from the bottom here. STL format allows you to use an STL format of a file that you would have generated possibly in a previous SolidCAM file. Maybe you're going from one machine to another and you wanted to save that geometry. This could be an STL file of a milling part that now has to be turned, or vice versa. Once you go to create your turning part, you can output an STL and then use that on a different machine completely. So it's just a third-party format to go from one file to another. If you had some unique stock that you'd like to turn on your machine, you can use 3D model. As soon as it becomes SolidWorks geometry, we can define it for many different things. And we can define unique 3D stock here just by using the 3D model. What I would suggest in that case is make sure that it's concentric with your model. That way, when you're turning it, you're turning the stock and the target around the same axis. Extruded boundary actually extrudes the profile of the part in the Z direction. So if you had some sort of unique revolved profile, prismatic profile, you can extrude that along the Z-axis to represent whatever unique shape you have, if it's some sort of extrusion that you're turning or such. On the opposite, you can do a revolve boundary around Z. So in this case, again, you have this chain selection window. You can actually choose your outside boundary if you've sketched it inside SolidWorks and revolve that around the Z-axis to get your custom stock. But if you don't have custom stock and you're just turning something simple, you can do a box definition if you're turning some sort of box stock, like so. You give it a length and width and height of that box stock. But generally, for turning, a lot of people start from bar stock or cylindrical billets. So we have the cylinder option, which allows me to just click on the solid and put a basic cylinder, length and OD and ID. And there's two ways to define that cylinder, relative to model and absolute. And really here, what we're talking about is incremental versus absolute definitions. For the relative to model, you'll see that it actually is adding material just on the faces and on the OD. So if I take a look at this in this turning point of view, we can see that I'm adding 20 thou in positive Z, which is where I put my coordinate system. We are adding an inch on the back face, so that right there is an inch. And then on the radial, we're adding 100 thou. There's 100 thou right there. When it comes to the ID, we can either add in the actual ID of the material, or we can do an internal offset. So again, from that internal face, we can add that 40 thou that I've defined there. And you can see that it added 40 thou on the internal diameter. If we go with absolute coordinates, it has the same controls here. All it's really doing is just defining the cylinder regardless of the original solid on screen. So we can actually give it the proper OD of the part. We can give it the proper length of the part. So this is 4 inches in length, but you'll notice these are still absolute coordinates. So that is from our Z equals 0. So to get that same 20 thou, I either create my coordinate system where I like it, the 20 thou, and then that's my Z equals 0. Or if I had it on the original face, this would have to be a positive number. This would have to be the 20 thou out. So really, again, it's just either you're defining the exact cylinder with the proper sizes here, or you could use relative to model, where everything is incrementally output from the face. So with that stock defined, I'm just going to use the cylinder option here. Once I click the green check mark, it actually parses the model. What that actually means is it's revolving that definition around the z-axis and then giving me a cross-section of it, a profile of it, for me to understand where the stock is, but only in the cross-section. And because this is a cylinder with an ID and an OD, it's really just going to give me this rectangular representation. Because again, when we're doing turning, we're only really looking at this top half anyway. For the target definition, all we're doing here is just selecting the solid. The solid on screen that represents the final part, we just need to click on that and then allow SolidCAM to understand that we're going to turn the stock into the target. But in terms of the definition of the target profile, we have many options on the side here. Envelope is similar to what we saw here with the stock. It's just going to give me this top half in the positive X direction so that I know where the cross-section of my part is with my tooling plane, my XY plane, XZ plane. But speed before accuracy takes a quick cross-section of that and generates a profile. And this is why it's defaulted. Usually that'll work. It'll give you the profile you're looking for your turning operations. But if you have a much more complex part and the target profile is just not generating correctly, you might need to take a more accurate look. Then you can click on accuracy before speed. This will take a closer look at those intersections, generate a proper target profile, and then you can use that in your turning operations. Instead of using envelope, if you wanted to do a section, this is literally a cross-section sketch in the XZ plane of your part. You would actually get a profile on the top and the bottom. And this can be useful if you're having trouble with the envelope or if you're looking to turn different profiles and you want to have the top and the bottom profiles. The drawback of the section is it literally is a cross-section of your part. So the fact that I put my XZ plane going down the middle of the keyway would mean that my cross-section does not include the internal diameter. It would actually cross-section with the top face of my keyway. So for turning, I'll usually just use envelope, speed before accuracy, and this time when I click on the green check mark, it'll continue to parse the model. But what it'll do is it'll take a look at this milled file, this SolidWorks model that could represent a milled part with flats and pockets and such that are not represented in the rotary profile, but in the process of parsing it, it gives me just the outside turning profile. So if I did have any flats or any pockets, once this thing spun, it'll just give me the outside edges of the spun looking solid. That's all I need for my turning operations. So once all that's done, I'll click the green check mark. And now I have the stock that I can reference in my toolpaths. I have my target profile that I can reference for the movements of the tool. For turning operations, because they are essentially stock recognition toolpaths, you need to add the stock and the target. Otherwise, you're really just doing finishing operations with no idea where the stock is. But if you'd like to see a step down and step over or any kind of progression with your toolpaths, it needs to know where the stock is, so it requires that stock and target definition. In addition to that, we want to make sure that the software understands where the jaws on the saw of the machine are going to be, and that's done in Setup. So if I double click on Setup, in the machine setup, you tell it which coordinate system you're working under. So in this case, I'm currently working on side 1, so I'll choose Mac 1. And I need to add some jaws. In this case, under Fixture, Name, right now I have it set to None. If I click on my little machine preview, we can see my stock and my target sitting in my machine. Well, what you'll see is actually it's recessed into the machine. That's because I don't currently have any jaws defined, and I'm actually defining this as being set up right on the table 0 of this machine. So let's start by adding some jaws to place this thing on the machine. We'll go to the 3 dots. 3 dots basically brings me to my fixture definition screen, and in the left menu we can define what type of fixture or jaws we'd like to use on this part. Under Define By, we have three types: Chuck Standard, Chuck User Defined, and 3D Model. If we go to 3D Model, what you're actually going to do is select the solid on screen that represents those jaws. This is a great way to get things like your soft jaws, your tailstock, whatever it is you're using to hold this thing in place. It could even be a cullet. Whatever you've got in terms of solid, again, once it becomes SolidWorks geometry, you can use it for definitions inside SolidCAM. So I would just click on whatever solid I have that represents my jaws, my tailstock, and then that would become the fixture I would use in my simulations and for my collision detection. If I click on Chuck User Defined, this is actually now looking for sketch geometry or contour geometry. And this window works the same as what we've seen on the milling side, where you can just choose solid edges if you have solid edges on your part, or if you have just a simple sketch that represents your soft jaws. You can click on those, and all it's going to do is give it some geometry down here. If we go to 3D options, you can see that it gives it some thickness, and then you can tell it how many there are. So you really just need to define the cross-section of one jaw, and then you can tell it how many there are and how thick those jaws are. But the one that's used more common is chuck standard, because this just uses the 3-step jaws. Really default shape, and a lot of this is just standard selection. You can see under clamping method, it asks you where on the jaws you're clamping on your part. So in this case, I'm clamping on the front corner. So that'll be my reference point for the placement of my part within my jaws. Clamping position, it will default to the outer diameter of your stock, but if you highlight that value, you can clamp on whatever diameter you like just by clicking on the geometry or by plugging in a number. But like I said, it clamps onto the stock by default because for this first operation, we're actually starting from the stock. So I'd like it to be on the OD of the stock. If I go down here, I can define the size of my jaws as well. So let's say we make this guy a little bigger for visual purposes. So that's the size of my jaw. And then again, 3D options down here, I can tell it how thick they are and how many there are here. So once I click the green check mark, those become the fixtures or the jaws that hold onto my part. And you can see now that it kind of brought it up a little bit. That's because the jaws themselves, the back end of the jaws, however I define them, they sit on the table face. So there's a couple things to note here in this machine preview. You have your table face, table station, represented by that coordinate system. And then we have my Mach 1 position 1 that I defined there. The Mach 1 position 1 currently is aligned with that reference point of the jaws. Because that is there, it pulls out the stock and target to match that line there. The jaws themselves are defined as being sitting right on the table. So that's why those guys are there and all that lines up like that. But in reality, I'm probably not holding onto my part right on size there. So that's what all these Z values are for. So let's go through this window real quick here. When I'm in this section of the machine setup, the Z controls the placement of the whole thing. So if I'm telling it that those jaws are a certain height above the table, that pulls up the stock and the target as well. So that full assembly is moved by this item right here. And the reason you have this is in case you're using those chuck standard or 3D model definitions. If you don't place them relative to your table, then they might be inside the table just like we saw a second ago. But if you're using the standard ones, those default as being right on the table. So that's probably a good place for it. I'll leave that at 0. In this indented area, I'm going to tell it what to do with Mach 1 position 1. So Mach 1 position 1 currently sits 0 from the reference point of those jaws, but I actually would like to hold that maybe a little further back. I can either do the same thing I just did with my mouse, so highlight that value and just roll with my mouse forward until I eyeball the location, or if I know where the location should be, I could type it in, or even better, SolidCAM always can be driven by geometry. So in this case, I'll just click on these 3 dots here. This allows me to pick Z. And now I can choose from the geometry. In this case, I probably would like to hold maybe just on the back end. So I'm looking to record the Z-axis of either this face, that point right there, whatever it is. Once I get a Z coordinate, you'll see that it shifts the part so that that point is coincident with the front face of the jaws. And then from there, if I'd like to, I can probably make this a little more machinable. Maybe I'd like to have some clearance. So I'll add 50 thou clearance, like make this 3.1. You can see that it shifted it some more. So on this mill turn, I'm actually setting up the jaws, and then I'm also setting up the stock and the target. All of that will help you with your collision detection, and it'll help you with the actual placement as well, especially if you're doing mill turn with the part, with a machine that can do 5-axis. That now understands that the pivot point is referenced right there. So I can put my Mach position anywhere I want in Z, and it knows that the pivot point is actually based off the machine. It knows that this machine pivots around that point right there. So I'll click the green check, the OK button, and then that defines that. And then later, after doing all my side 1 operations, if I'd like to add operations for side 2, I need to tell it that we're working under side 2. So I'll right-click on operations, go to machine setup, and I can put one at the end of the tree, and then just repeat the same process, but this time under Mac 2. So we're using clamping fixture, set to 0. We're actually setting this up for number 2. I'll click on the 3 dots. This time, I'll probably be holding it on side 2. You can see the coordinate system. Probably hold it up to there. Click on the green check mark. We can look at the machine preview. And then it's holding on there. Now, the diameter is still the same. So what I'd probably like to do is change that to a different set of fixtures as well. So I'll go back to the 3 dots. And you can see that the jaws are facing in the direction of Mach 2 now, but I want to change that diameter. I'm going to change it to that location there. And then let's just make these guys the same. Okay, so same jaws, holding at that diameter, and then holding at that Z position. Now the stock is still being shown in this machine preview, but the placement of the jaws relative to the target is what we're looking for in this window. So now that would allow me to do some turning on side 2, all in the same part file. So in this one file, my mill turn part can be done side 1, side 2, or multiple setups as well. If you're doing an extra long part, you can add as many of these setups as you need for the different setups of how you're going to do it with your steady rest or tailstock or whatever you're doing. So any questions on this or anything else from SolidCAM, just give us a call at 1-866-975-1115, extension 2, and stay tuned for the rest of the videos in this introductory series. Thanks for watching.